Okay guys, this is problem 2.3 out of Griffiths Quantum Mechanics textbook. Now before I start this problem, I just want to say that if you wouldn't mind please liking this video and subscribing to my channel, I'd really appreciate it. I post a lot of videos that work through solutions out of common undergraduate textbooks, so I think a lot of the material I post will be helpful for many of you. In addition, it's the free, easiest way to support my channel and what I do, so I'd really appreciate it. With that out of the way, let's actually go through solving this problem. Problem 2.3 says, show that there is no acceptable solution to the time-independent Schrödinger equation for the infinite square well where e, or e less than 0. This is a special case of the general theorem in problem 2.2. So I've done that problem on this channel as well. It essentially said that E has to exceed the minimum value of your potential energy. In this case, inside the well, it's 0. So we're looking at cases where E is also equal to 0, in which case it's not exceeding our potential, or even E less than 0. So just to remind you, Schrödinger equation for an infinite square well is just minus 2m e over h bar squared, because our potential is of course 0. And since this is just a constant, we can define it like this, where k is the square root of 2me all divided by h bar. Now our boundary conditions for the infinite square well, just to remind you, is that psi of 0 equals psi of a, which equals 0. So this is 0, this is a. Our potential goes to infinity here, and it's 0 inside the well. So we need to know that as well. Now if we look for the case where E equals 0, well, obviously if you plug in 0 for E here, K isn't equal to 0. So then our Schrödinger equation is just this. And that tells us that the first derivative of psi with respect to x is equal to some constant, call it c. And this is a pretty easy differential equation to solve. You get psi of x equals cx plus b, where b is just some constant. Okay, well, psi of 0 has to equal 0. Now if we plug 0 into here, then psi of 0 is just b. I don't need Siri actually. Sorry, just updated my iPad. So we get b equals 0. So then psi of x simplifies to just c times x. But now let's apply our other boundary condition. Psi of a equals 0 equals c times a. Clearly a is not 0 in this case, which means c has to be equal to 0 by the zero product property. So then psi of x is just 0, which is the trivial solution. And if you remember, we're not actually interested in the trivial solution. A little bit different, but let's say e is a negative number, less than 0. Well, again, our Schrödinger equation. And you may say, well, that doesn't make a whole lot of intuitive sense for the energy to be 0, but let's just kind of work through the math of it. I think that's really what they're trying to show. Okay, so in this case, we can call this k squared. And in this case, since E is less than 0, Maybe I should do this in a different color so you understand. We'll do it in this color. Since e is less than 0, this is actually going to be a positive number now. Now, if you remember from differential equations, this is just a pretty simple second order differential equation. You can solve your characteristic equation. That's my dog walking by. If you hear him, sorry about that. Lambda squared equals minus 2me over h bar squared. And just keep in mind that this is a positive number. So then lambda is minus 2me square root over h bar, which is an element of the real numbers. There's no imaginary number because the e is also negative here. Now, if you remember having real roots, this is technically a plus or minus. If you remember, when we have real roots like that, the solution to our second order differential equation is just c1 e to the kx plus c2 e to the minus kx, where the plus and minus are our two roots. In general, the solution to the differential equation would look something like this. Hopefully you've seen that before, but if not, hopefully that jogged your memory. Okay, so we have this differential equation, and let's apply our first boundary condition, which says psi of 0 has to equal 0. E to the 0 is just 1, so this is just c1 plus c2. So we can express, for example, c2 as just being minus c1. So now our wave function psi of x can be expressed as c1 times e to the kx minus e to the minus kx. Okay? Now, this term is just 2 times sinh of Ka. Just by our definition, how we define hyperbolic sine. And the 2, which is just a constant, can be absorbed into C1. So we'll say psi of x is this new constant. We'll still call it C1, even though it's technically different. Times sinh, Kx. Okay. But we have one more boundary condition, which says that psi of a has to equal 0, which is C1 sinh of Ka. Now, sinh looks something like this. Kind of looks like your cubic function, actually. Just say sine of x. And it's 0, so sinh of, in this case, Ka equals 0 when Ka equals 0. But this is a problem. Just like before, we know a is not equal to 0. And k is also not equal to 0. Remember, this is the case where e is less than and not equal to 0. So m is not 0, h bar is not 0, so k is also not equal to 0. So the only way that this could be true is if this constant c1 is then equal to 0. But just like before, that leaves us with the trivial solution, psi equals 0, which is not what we're looking for. So that is showing that these energies are not allowed. They're not solutions that we're looking for from Schrodinger's equation. So I hope that helped you understand this problem a little bit. And if it did, please give me a thumbs up and subscribe, and I'll be sure to post more solutions. Thank you.